Hello everyone, welcome to Machine Learning Session 4. I am Ashutosh and I'll be taking this session on linear regression. In this session, we are going to teach you to build an entire model by yourselves. Um, we are we are going to avoid using functions as much as possible, but we got to use them, so it's not the choice. But we'll try to make it as raw as possible. Yeah. So before we dive into making the model, let me give you a good head start. So I'm sure you're bored of the introductions about what is ML, what is this, what is that. But anyways, just for clarity, let me give you just a quick refresher. So on the normal computers, like normal as in a calculator, you can say, you have input, you have a predefined process like an addition, multiplication, subtraction. I mean, you know it, right? What you have to do. 2 into 2, 4. So this is the operation. I mean, you know it here. In here, in ML, what you do is you predict. Suppose you give 2 to the machine, to the ML model, and you need 4. You know the operation is 2 plus 2 equals 4. The machine doesn't know it. The machine has to learn it to find out. So how would we learn it? Imagine teaching a child, not in the similar sense, but like suppose there are multiple breeds of dogs. How would you differentiate between them? Using multiple examples, right? Like there is Pomeranian, there is Golden Retriever, and all that. To distinguish between these, you need a lot of pictures of Pomeranian, Golden Retriever, and different huskies to differentiate between them. So similarly, to teach a ML model, even simple things, we need a lot of examples like 2, 4, 3, 6. Let's make it multiplication. 4, 8. Okay. So this is a simple thing. Now, as a human, you can see that this is y equals to x, right? Remember you were learning linear regression? We're currently targeting linear regression, right? Linear, this is a linear equation. Y equals mx plus c. Alright, this is c if I remember correctly. Now, okay, so that is the basic linear equation. Now, how would the data look like? Let's say x 3, 6, 4, 8, 5, 10. Okay, so the data is given in a format. You can't just feed data like abnormally. Like, let's say you send data in a single stream, like 2, 4, 3, 6, 4, 8, 5, 10. This thing won't work. You need to feed it data in a proper format so that it knows which it has to predict and which is the input given to it. So, okay, let's make a graph for this. Okay. Yeah, so 1 gets 2, 2 gets 4, this gets this gets this. Okay. Now, to predict like this value, let's say here is 12. To predict 12, you're gonna need 24 here. How would you predict that? You would make your line, like you would get the equation, right? You would extend the line and then you would just find the intersection of this and this, then go here. 24. That is the standard thing. Well, the machine does exactly that. We mean the real world data is not exactly like this 1 into 2 like this. The real world data will be something like this. Let's say here there is a point here, 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 maybe there is a point here. So to best predict this thing, we draw some line. This may be line 1, this may be line 2, this may be line 3. Notice notice this thing. For each of these lines, I mean, you get a distance from the points to a line, right? So this is the error in our prediction. Like the model will predict this green line. The model will predict this green line. Yeah. But the actual data points are these. These are the actual data points. For this example, consider the line name numbered 1. Alright? Yeah. So this is the error in our prediction. This big line is the error in the prediction, these lines. Now, consider these errors as loss. I mean the loss in the original value, right? If the, okay, let's say here we have L1, L2, L3, L4, and so on. These are the losses. We have to minimize the sum, like L1 plus L2, Ln. We have to minimize this. I mean, the smaller the sum is, the more accurate our model is, right? The more accurate our prediction is. If you're predicting something, you have to guess it accurately. The more accurate you are, the better the thing is, right? The better your guess is. So this is not like wishful guessing, but something like that. Each model, each model works to minimize this loss. Now, okay, so yeah, that is the basic goal of every possible thing you will learn in machine learning, deep learning, any direction you move forward in this. Yeah. So now there are different types of models. Some models we feed everything. Like we have our input, we have our output. We feed everything into the model, right? And sometimes we just feed the input. We don't even give the correct output or anything. So this here we are controlling both of them, right? The input and the output given to the model. This is called supervised learning. This thing is called unsupervised. Now, as you move deeper into ML and into DL, everything will go to unsupervised. I mean, this is the boss. Supervised, it is used, it is very prominently used, but yeah, as you move into advanced things, this will be the game changer. Okay, now let's look into the resources we are going to provide you. So let's look a bit into that. So this is the Jupyter notebook we're going to follow in the session. I'm sure all of you are already familiar with this Jupyter notebook since it was introduced to you since session 1, I presume. Okay, so what is machine learning? It simply means teaching a machine how to think. How to think. Yeah. How does machine learning work? You collect data. I mean, to collect data, I mean, you can't really feed random data into the model, right? I mean, I showed you here. You can't really feed data like this into the model. This is just wrong, completely wrong. Yeah. So Now, preparation of data. I'm sure all of you remember from the EDA session that sometimes the data points are missing. So we also have to deal with them. If the data, if the missing data points are really less, then you can just remove them. If there are quite a few missing data points, then it is either a bad data set or you have to deal with them. You can either fill them with minimum values, some kind of average value in the column or something like that. So choosing a model, we are not going to deal with that now. Training, evaluation, deploying. Yeah, we're going to do all that later on. First off, my job is to teach your machine how linear regression works. See, in supervised learning, we get training data and testing data. Training data, the machine will take this as input, it will predict something, and this is the testing data. The machine will test the predicted output against this testing data. Let me give you an example of this too. Okay, so you have 2 in your data and the output is 4. I mean, you know this is the output and this is the input. This is the model, alright? So you know how humans guess? I mean, the guess is random, then you give some hints, it gets more accurate. Well, something in the similar sense works here too. You feed 2 into the model, and let's say it predicts 2. Yeah, it predicts 2. Uh, for randomization, let's say 3. It predicts 3, but the testing data, the output data is 4. We know this. We know this. Now what the model will do is minimize this. 4 minus 3 is equals to 1. I taught you about losses earlier, right? So machine will try to minimize this. Let's say in the next guessing turn, the machine predicts 3.15, so the loss is like 0.85. This is better, right? Okay, so this is a supervised learning model. In case you weren't clear earlier, this was the thing. Now for unsupervised learning, you notice you just provide inputs without knowing the right answer, the initial right answer that you provided in the supervised model. Here the machine has to figure out everything all by itself. Reinforcement learning, yeah, this isn't for now. And the applications of machine learning, I'm sure all of you went through it in the first session. I'm not gonna go through these again. Okay, so the code starts here. None of my job is this. Okay, let's dive into linear regression. I think all of you are ready given this much explanation. It's fine, I guess. Okay, so we have a graph. I'm gonna do it like this. Yeah, we have a graph. The graph has a few points. And this is the line, I guess. It approximates these points. Approximate. This is not a prediction or anything. This is just an approximation line. Yeah. Now this will look like y equals mx plus c. That is the basic line, right? If you have x, you get y. You have x, you get y. Now here we only have a single x. Now this x is called the feature. This is called the label. Now here we only have a single feature. We can have multiple features, x1, x2, xn. So here y will be a result of mm, m1 x1, m2 x2, mn xn plus c. Hmm. So this is the approximate line, right? Let's make it as y hat. Let's the original equation was, I don't know, let's make all these hats. Hmm. Hat we're going to use for prediction things, right? Yeah. So let's say the original one was like the actual data, like the actual equation that fits into our data was like this. Now here our loss will be y minus y hat. This would be a loss. This one equals m1 minus hat and so on till mn minus m1 hat. Yeah. Okay, so this is a loss. Now, if the machine gets something wrong, we have to punish it, right? Just like a child. So now it matters how much we punish it. The loss is, let's say, a here, right? If we punish it only for a, like consider the punishment as a quantity, if we punish it only for a, it's fine. For current scenario, it's fine. But what if we want the machine to learn faster or more better? It's a tested and researched trend and technique, so don't really ask me about this. But what if we square this out? What if we square this out? Here, the punishment gets exponentially larger, right? So let's see. Now, if the loss was 2, for this, the loss is 4. If it was 3, it is 9. If it was 4, it is 16. 5, it is 25. You see how exponentially the loss grows? Sometimes, if the loss is like 2, 3, 4, the machine will make very minimal changes to itself to fit into our data. But here, since the loss is very, very big, the machine will make some good changes to itself to be more accurate. Okay, so back to this. This is y, this is x, and these are points. Yeah. So we have to predict these points. We made some approximation line based on our observation, but the machine might not necessarily predict something like this. The machine might predict something like this, something like this, or even something like this. And this is very, very bad. This is a very, very bad prediction. If you just predict this, just go and die somewhere. So now back to this. We have to minimize these as I told you earlier. So there's that. Okay, so I think we're done with the linear part. Now let's move on to use of y equal to mx. I mean this thing doesn't necessarily fit everywhere. We have to go into higher degrees to fit even more erratic data. That's something like this. See, we go to something here. We gotta make polynomial equations. So they will be curves. This thing is linear. This won't work everywhere. In polynomial equations, you know y is equal to mx plus m1 x square. Yeah, x square. Something like this. The y depends on degrees of x. So the loss will be something like this. I remember the hat notation I draw. I just taught you earlier. So mm, we have to minimize this. How do you minimize higher order equations? I mean, after all, it is algebra, right? Remember in J when you were taught like differential equations, you had a function. Now that is pretty simple. This one, yeah. So how do you find the minimum of this? You had to first do the first order differentiation, then a second order, so that you would find the minimum, right? That is exactly what we do here. We differentiate this equation. We differentiate this equation and get our minimum values. So here we're differentiating multiple times. I mean, just for second order you have to differentiate 2 times. So this will be something like in real world data set, let's say the degree is something like 156. That's pretty high, but yeah, something like that can happen. So 156, you can't just keep differentiating. That will be computationally very, very expensive. So what we do, we check like, okay, for 156 I can't really draw a graph, but imagine this is a surface. Yeah, this is a surface. Oh, this. Yeah, look at this one. So let's say our equation yields this. This is the surface. Yeah, not really multidimensional, but just for clarity. So in the first differentiation, let this is the loss. This is the, I mean, what do I say? This is the loss function. This is the loss function in the, this is the loss function visualized. Now, for gradient descent, no, ignore that term. We're minimizing the loss, right? Minimizing loss using differential equations. So let's say the loss was here. We minimized it, it came here. We again minimized it, it came here. It doesn't necessarily go this way. It can go this way, it can go this way, it can again come here, 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 it can again come here. Yeah. So when you differentiate in the first turn, we decrease the loss a little bit. Again you perform the differentiation, you decrease this one a little bit, you decrease this one a little bit. It might decrease in this direction a little bit. So it progresses like this. You might have a question. Initially, we don't give the machine anything. So on what m? So the machine needs an m to differentiate on, right? Some coefficients. What does the machine, where does the machine get the m from? The thing is, this is randomly initialized. In every time you train the machine to decrease the loss. See, this is the loss, yeah? Every time you train the machine to decrease the loss, the machine decreases its m. Initially, it's random, then it goes to like, let's say m dash, there's not really a definition, just a different value of m. And it changes for every coefficient. Let's use m dash I. In the second turn, m dash dash I, so this goes on and on and on. And we have no guarantee that the machine will reach this point. We have no guarantee. The machine might as well come and stop here at this point, but it may not reach you. It totally depends on the initial random values and several other model parameters that we are going to teach you in. We are going to teach you later on. So basically that was the gist of the initial machine learning models. This thing is called gradient descent. Let me change the color here. This thing is called gradient descent. And if you want to be a machine learning engineer in the future, this this thing should always be in your mind. Like you should never forget this. This is basically the building block of every model. Everything you're going to learn later on, neural networks and all that, especially neural networks, this gradient descent thing will be really clear. And if you aren't really clear here, you can also watch a video from a professor, not exactly professor, from a tech enthusiast, V Blue One Brown. He teaches this on neural networks and he explains it with animations and all that, and it's really amazing. So I suggest every one of you who's watching this session to give it a try. The videos are short, 20-30 minutes. Yeah, so you can give them. Now a few more things before we dive into the model building. Cross validation. Okay, so we have our training data and our testing data. Both of them go into the model. The model initially predicts against the testing data and the loss is minimized. So that is the normal thing. Now here we take training, we take the training data, 70% of both of them, and train the model on that. Now, how do you validate that the model will actually perform well on a real world data set? The only way to do that is to evaluate the model on data it has never seen before. And where do you get that data from? 30% of the training data. It has never seen this, right? The model has never seen this. And we also have 30% of the testing data here. So we pass this training data onto the model to predict only the training data. Remember this. Onto the model will predict something. The model will predict something, let's say y hat. This y hat is tested against this 30% testing data. Now we know how the model performs on data it has never seen before. This is the actual performance of the model. This is the actual performance of the model. And this should be, you should strive to make this as better as you can. Okay, so I guess that was it for linear regression. And if any of you have any doubts or anything, you can just tell me in the comment section. We might as well put another video if a lot of doubts come up. And as for resources, this notebook, this notebook will be shared to you in the description of the video. Yeah, so the code will be done by another of my colleagues. There is also another book I would highly recommend to each and every one of you. So this is the ISLP book. This is the ISLP book, Introduction to Statistical Learning in Python. And this is a very nice book. This is free and open source. Anyone can contribute to it and anything. So yeah, that is it from me. Another one of my colleagues will be taking it from here. Thank you, and I hope you had a good time learning about it.
Hello everyone, how are you all? Hope you are all fine. This is Sayam Gupta. In today's lecture, we will learn about the implementation of a machine learning models as well as using of a scikit-learn to implement those models. So without any further delay, let's move toward the section of what we will cover today's lecture. So what we will cover? We will cover machine learning concept to hands-on coding as well as we will learn how to implement linear regression model from scratch and by using famous library called scikit-learn library. I will also I will also provide you the documentation of a scikit-learn library at the end of this lecture. Topics we will cover in today's lecture are regression-based house price prediction and classification-based diabetes prediction. Now let's go to the roadmap of the notebook. Before going to the coding part, I will tell you briefly about the roadmap we will follow in this lecture. Now let's go. Now let's talk about the roadmap we will follow. Now let's talk about the roadmap we will follow in this lecture. First, we will create the setup by installing the libraries. If you are doing this in local environment, you need to install the required libraries before importing those libraries, and then we will prepare the data. You can prepare your data directly from the libraries, or you can directly download the those. Now let's talk about the roadmap. Now let's talk about the roadmap we will follow in this lecture. First, we will create the setup. For creating the setup, we will install the required libraries. If you are running in local environment, you need to install the required libraries before importing those libraries. For installing libraries, you need to do this pip install, pip install. For example, you want to install NumPy, you will write NumPy. If you want to install Pandas, you will write Pandas. After creating the setup, we will now prepare the data. For preparing the data, you can directly import from the libraries. There are various data sets. You can import from directly the libraries from the scikit-learn, or you can use dot dot read CSV, or you can read the files by downloading those files in local environment. After preparing the data, we will do EDA, escalated data analysis, so that we can understand our data before we are applying those models. After that, the main part, which is implementation part, we will create the function for linear regression model, linear regression model, and then for MSE, mean squared error loss, and then after mean squared we will create function for gradient descent algorithm. MSE loss is used for creating the loss, creating the for getting the details between the actual value and the predicted value. Supremacy loss is actually, in a short, in a brief manner, is a, is a difference between your predicted value and your true value. And gradient descent is used to decrease the used to decrease our loss decrease our loss by changing our weights and biases. For weights we will use the term M, for signifying. For biases we will to use B. After doing this we will train and test train and test the models. After training and testing we will visualize the results. After visualizing results, I will also tell you and visualize you the gradient descent path that is followed by the model. So now let's go back to the coding section. Let's come to the coding part. First we will create the setup. We will import NumPy library which is used for mathematical computation. We will also import pandas library which is used for creating data frame for data analysis. We will also import matplotlib for visualization for better understanding of our data. We will also using MLP tool for visualization of a gradient descent algorithm, which I will tell you further in this lecture. We will creating a random seed so that the values of mismatch between the values between you and me will not change. Go to the data preparation part. We are taking house price prediction problem because we all are familiar with house prices and how house prices are varying. Since you are all familiar with square feet, area, bedrooms, or prices. What is square feet? It is the area covered by the house. What is bedroom? Numbers of rooms. Numbers of rooms. And what is price? The price which we need to pay to get the house. So we are creating a dictionary with a key and their values. We are for every for every house we are we are creating we are creating a square feet area, the number of bedrooms, and the prices for that house. We are creating a data frame from this dictionary. Now we are also using feature engineering. Feature engineering as a part of data science, in which we try to create new features from existing features. For example, here we are creating square feet per bed, which implies that area covered by the single room. As you all already know about the 1 BHK, 2 BHK, 3 BHK flats. What does those mean? Three bedrooms, one bedrooms. That is why we are also using bedrooms. Now let's see the top five houses. See here five houses with their area and the number of bedrooms and their prices and for each bedroom, for each room, what area it will cover. It is covering. So let's see the house data. We've already seen the house data. Now let's come to the exploratory data analysis part. Before diving into the graphical part, we should the firstly see the data frame. How many columns does it have null values or not, or how is the correlation between each values. As you can see, we have only four columns, and one is the target value price, which which we will predict. As you can see, square feet per bed has a float 64, which is the different data type, and the data type for all three are in 64. You can also convert into in 32, but if we convert into in 32, some package may be lost. Package means some data may be lost. However, it doesn't concern since we are since the values are in the range of point 3.4, so they will not incur any more damage or more loss in our prediction. Now let's see the correlation between each feature. Since all the features are integers or numericals, we are directly using dot core. Dot core only works for numerical data. So if there is a categorical data, you need to remove the categorical data before before using this correlation. Now let's see the analysis of each column. The mean value or the mean area covered by most of the houses are 2200 square feet area, and the standard deviation is 460. And the minimum area covered by any house is 1500, and the maximum is 3100. So values are didn't change so much. And for bedrooms, the maximum bedroom we have is 5, and the minimum bedroom we have is 3. And the prices ranges from how many? 1,58,000 to 5,40,000. Very huge. And the me and the and for square feet, but 500 to 6 cities is not so. See the heat map. Heat map is actually the correlation metric in a graphical form. So we are seeing the correlation metric in graphical form. Here we can see square feet area versus square feet area as a one. Of course, they both are same. Of course, the relation between both will be same. And the relation between bedrooms and square feet is 0.93. So much. The more the value is tending towards one, the more they both are the function of each other. For example, the square feet is a square feet. For example, if we take square feet as a y, then y is the function of a bedroom. Bedroom, for example, we take as y can be function of the bedroom 0.93 times. For example, if we increase the square feet area by 2 times, then bedroom area will increase by 0.1, 0.8 times. So this is the correlation matrix. So I have a question. What is the need of a heat map and what is the use of data frame dot correlation? So hope you all know. If you don't know, try to search and see what is the need of a heat map and why we use dot correlation. Now we will analyze various features. So first we will bivariate analysis. We do the bivariate analysis. What do you mean by bivariate analysis? Bivariate analysis is analysis in which we analyze between two features, relation between two features. There is a univariate analysis. We analyze the one feature. There is a multivariate analysis. We analyze two or more than two features at the same time. Now we are using bivariate analysis. We are analyzing between two features. We are analyzing square feet area versus price. Whereas we are also analyzing bedroom versus price. We are also analyzing square feet head versus price. We are seeing the as the prices increases, as the area increases, prices also increases. As you can see, as you can see, the as the area increases, the price also increases. And for the bedrooms versus price, as the bedrooms increase, also prices increases. As you can see, for 3 bedrooms, we have the prices range up to 150 lakh to 250 lakh, and for 4 bedroom, I have 250 lakh to at least 370 lakhs, and for 5 bedrooms we have prices are from 4 lakh to 550 lakhs. So of course, as the bed numbers of rooms increases, the price also increases. So now we are seeing square feet per bedroom for 1 bedroom prices. As we can see, as the area for 1 bedroom increases, prices also increases. But you can see here, they sometimes also not increases. As you can see, we have a high number, we have a high number of, we have a high area of a bedroom, but our price is low. So here the data is not his data is not well distributed. As you can see, maybe correlation also not good. Yes, you can see the correlation between square feet versus price versus accuracy, price versus square feet per bed. You can see point 2. As you can see, there is not so much good relation. That's why we are seeing this graph. Now let's talk about multivariate analysis. We are using pair plot for multivariate analysis, or we are directly feeding the data frame into the pair plot since we are analyzing between various features. Firstly, we have in x-axis square feet, bedrooms, price, square feet per bed. In y-axis, in y-axis, square feet per bed, price, bedroom. This graph and this graph and this graph and this graph. These all four graphs are for a single feature. For example, for square feet, this graph is given. For bedroom, this graph is given. For price, this graph is given. For square feet per bed, this graph is given. So what do we mean by all this here? For example, we are taking square feet per bed. As you can see, for 500, the number of for 500 and for 600 for 700. As you can see, as we increase in the square feet per bed, the numbers of values, the numbers of values between 500, the number of value between 500 600 also increases. For example, there are values for 600 more than the values for 500. For example, we have a 3 values for 500. Then for 600 we have 5 values, and for 700 we have 2 values. So since the distribution in this way, we are seeing this graph. Since the distribution in this, we are seeing this graph. Can you tell me? Can you tell me about this graph, or have you encountered this graph before in the previous session? If yes, can you tell me what is this graph? Is I have also the question for each figure. Is it well distributed? If yes, then what these features are called? These features graph are called. If you don't know, these features are distributed in Gaussian way. This is called Gaussian distribution. And when we have a Gaussian distribution, features in a Gaussian distribution form, then we have very good distributive data. So data is very good. It can fetch us a very good ML model. So always try to have a data in a Gaussian distribution. If you don't have a Gaussian distribution data, what you are doing? For example, if you have a skew data, for example, we have more numbers of data in the right hand side. For example, more data in 7. For example, more of numbers of data 700. So what you are doing? What we will do? You will use a thing called np.log of the exposure, which will which will make our data again Gaussian in Gaussian way. Hope you learn this method beforehand. So I am not telling you more about this. If you want to know about Gaussian distribution skid, you can also you can also you can also search them. What is Gaussian distribution skid data, skid features. Now let's come to the most favorite part, regression task, building a model from the sketch. Now we are building a model from the sketch. Firstly, we will create the prediction function, and then we create the loss function, and then we create the gradient descent function. Before we creating this function, predicting function, loss function, gradient function, let's go back to the notebook and we see how we are how we are implementing this function. So let's go. Now let's talk about the linear regression function. The formula for linear regression function y equal to m times x plus c, where m is the weight, c is bias. Sometimes we refer c as a b as well. In some text, here we are written here it is written as a b. Both mean same. X is the feature, or you can call feature vector. In our house-wise prediction task, house-wise prediction regression problem, house regression problem, we will taking single feature for proper understanding and less complex function formation. Feature we will use square feet, which is area covered by the house for predicting prices of the houses. For example, let's take the example how our function will work. For example, for house number 1, we have 1200 square feet of area, 3 bedrooms, and 400 square feet per bed, as well as the price in 1,62,000. Now, initially we are taking M and C value, or you can write M and B value 0, 0. Both are initially 0. So our prediction function will predict y pred, which is equal to y cap is equals to 0 into 1200. X is the feature. We are only using square feet, only single feature. We are not using single number of bedrooms and square feet per bed. Y is equals to 0 plus 0, which is equal to 0. So difference between y true and y pred is what? Can you tell me? Yes, it is true. The difference between y true and y pred is 1,62,000, which is a very huge quantity. So how we can predict more accurate or more near to our y true value, which is actual value of the price of a house? So here our gradient descent algorithm comes and it will compute the m and b value, the hyperparameters value, so that our y prediction function will predict y actual value or price of a house very near, very accurate to its actual value. So after computing the algorithm for 1000 for 1000 times, our y true value is 137. Our m value and b value is 137 and 0.5, which I will tell you later in the code. So now our difference will what? Let's compute the y spread value, or you can see y cap, which is equal to 137 into how much? 1200 plus 0.5, which is near to 164,000, 1,64,000. So our difference is now what? Only 2,000. And also the loss, how we compute the loss? Loss is actually the square of the difference, which is the square of the difference and the average. So average is what? We are taking only single value. We are taking only single house. So the number of house is 1. So our loss is the function for loss is actually this, which is the average of a sum of a difference between y prediction and y true value square. Y true minus y pred square. Y. Now let's talk about the prediction function. Here we are taking 3 parameters. Here m is the weight, b is the bias, x is the feature. Since we are taking single feature, y will be what? M times of x plus b, where m is the slope of a weight line, b is the bias, x is the feature. Here what feature we are using? Square feet. On a y is what? Y is the, we are writing the cap so that it is a y predicted value. Y is the predicted value of a Hackslash. Now let's come to the mean squared error loss, which we have already learned and talked about before. What does it measure? It measures the average square difference between y true and y pred value. The loss function, I have already told you, is average of a square of a y true and a y pred value, which is, we can also write that average of a difference square. Go to the, now let's come to the gradient descent algorithm or function. algorithm or a function. What is the use of a need of a gradient algorithm? It is is used to calculate hyperparameter hyperparameter after every loss is complete. After every loss computation, loss computation, it helps in here. It helps us to give the value, help us to update or give value to m and b. How we are calculating m and b? We are calculating m and b from the loss function. Now let's talk about the loss function. Loss. How is our loss function? Loss function is mean squared error loss. What is the function? It is average of a square of a y true minus y period summation to n. We can also write this loss function as this. We can also write this loss function as this summation I equal to 1 to n y true minus y period whole square, which equal to 1 by n summation I equal to 1 to n y true minus m times of xi plus b whole square. Since our y prediction function is what, m times of xi plus b. Now what we need to calculate, what we need to do, we need to minimize the loss. Minimize the loss. Why do we need to minimize the loss? We need to minimize the loss so that we can have a accurate, accurate prediction, or you can say prediction prediction prediction. So we can have accurate prediction, or prediction very near to the actual value. So how we can compute the, how we can decrease the loss function by changing m and b. Do you think of any tool so that we can do? Think it and tell me. If we are saying we can do using calculus. Yes, that is true. For change for calculating the value of m, calculating the value of m, we can derivate the loss function against m and derivate the loss against b for finding m so that loss will decrease and b so that loss will decrease. So in for calculate. Now let's calculate for m. Now great. Now derivative of a loss function with respect to m is what? Minus 2 by n summation I equal to 1 to n y true minus m times of xi plus b. And for b del j gradient with respect to b. Gradient with respect to b is minus 2 by n summation I equal to 1 to n y true minus m times of xi plus b. Here I have not written a term which is called xi. Xi is in multiplication for derivative of a loss function with respect to m. Let me write it. How we are calculating the derivative? By using chain rule. By using chain rule. Hope you all know chain rule and can compute this without my help to do everything. Now we have computed the gradient descent, and this formula we will use in compute gradient function. Compute gradient function for calculate for changing the m value. We are using m equal to m times minus alpha times of del j by del m. where this is what? It is gradient descent of a m, descent of a loss function with respect to m, in descent of a loss with respect to m. Alpha is what? It is learning rate. And for b, also b is equals to b minus alpha times del respect to del b. So in this way, we are computing the gradient, computing the for each epoch, for each loop, you can say epoch or loop. For each epoch or loop, firstly we will compute or we will predict, 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 predict on extend data, and then we will compute MSE loss, MSE loss, MSE loss by giving y true value and y cap value. After computing MSE loss, I will compute gradient. After having gradient, I will change the parameter m, which is m equal to m minus alpha, which alpha is here learning rate, learning rate of gradient of m. Similarly, I will change the b is equal to b minus alpha times of gradient of b. After changing this, I will compute compute loss for y testing data, y test true, comma y pred test, testing of testing data. Before loss, I will need to predict on. I need to also predict y cap for test yt yt pred test. Don't confuse between this. I have written y plus yt slash spread, y cap plus or y plus slash spread, both are same. I am predicting on access test data. Access data. For I am predicting on access data and I will calculating the loss. This this is doing for training data, and this is we are doing for testing data, and this is the way which we are our training or testing loop will perform operation. Now we are taking the 14 number of samples, and after 14 number of samples we are taking extent, which is equal to trained year, which is a y train, which is equal to price of the house for each house. X we are taking the next 6 samples and their square feet area, and y test for price of the 6 houses. You can see these bedroom and square feet weight are not in the X train or X train or X train. Price is Y value, which is Y train or Y test. For Y train is this. These numbers of values are in this. For this price column, for this all 14 number of samples are price Y train. This is Y test. This is X train. This is X test. Now we are changing. Now we are getting the learning rate, which is equal to 1 e raises minus n, which is 1 e raises 10 to 1 into 10 to power minus 9, 1000 of epochs, wherein slice the m or b parameters to 0 0. We have created a list for training loss or testing loss or parameter history. As you can see, for each epoch, we are predicting on training data with M or B value. Since, as you can see, we are globally in this slide the M or B parameter. For every epoch, our M or B changes. Yes, you can see, for every epoch, our M or B value changes and it is in global variable. Global means it will change for globally. We are computing the train loss and then after computing gradient, we are changing the m value, b value, and then we are calculating the testing loss. And after calculating the testing loss, we are appending those test loss or parameters value in every epoch. But now, for after every 10, I will also printing out printing out the train loss, test loss, and the m or b parameters so that I can understand how our model is going. Or after, since our history is there, we are converting those parameter history into array. As you can see, our first initial value of m is 12. Actually, it is 0 or b is 0. But after 10 epochs, our testing or training loss is this, and m or b value is this. As you can see, the more the loop is increased, the more that we are training and testing, the more m or b increases, or the more less the training or testing loss will decreases. As you can see, how heavily training or testing loss decreases. As you can see how tiny loss decreases. Since the data set is not well defined, we are seeing a huge quantity of training or testing loss. Normally training testing loss ranges around lakhs or thousands or 100s or 200s. The less the training loss, testing loss, the more we have a good amount of value. Now I will tell you about a training or testing curve. Here you can see the training and testing curve. What can you infer from this training and testing curve? Can you infer something from training and testing curve? You can see the MSC loss and you can see the number of epochs. After 400 epochs, you can see now our MSC loss is not decreasing so much. So you can say after 400 our model is also not learning. So why we are doing this? You can compute the same thing at 400 loop as well. Since we are not training, so these numbers of loop are not needed. However, sometimes our after full learning, our model sometimes like de-learning as well. It is our loss will also increases sometimes in some cases. Here it is not increasing, which is a good. By the way, it is not so much decreasing because our learning rate is so less, which is 1 is to 10 to power minus 9. So that's why it is not so converging. Now we have three cases for training and testing loss curves. One is the case of underfitting, another is case of generalizing, which is the ideal case we always refer to, another is the case of overfitting. Now let's get back to Node and talk about this. Now let's talk about the three cases. First is the case of First is the case of underfitting, and this is the case of ideal case which we all need, every ML engineer loves, and this is the case of overfitting. As you can see here, our loss, which is the this all curves are loss versus epochs, number of loops, or red is for training loss, or this is for testing loss. So here you can see our data not learning very good. It is not learning very good, as you can see. So here the model is underfitting. There are so many cases that our model is underfitting. First case is we have a less amount of data. As you can see, we have less amount of data. However, sometimes this is also due to our hyperparameters tuning, or our the initial values of hyperparameters. This can also occur during using bad or using irrelevant hyperparameters value. However, fitting will remove by increasing the number of epochs. Ideal case is where our model is learning as well as training and testing loss both decreases. Then here is the Here is the case of overfitting. Our sometimes our model doesn't learn on the training data. Here you can see firstly model is learning, but after some time it is not learning. You can see testing loss after some time is increasing. This is due to our model overfits on training data, so it doesn't follow the general train. So these are three cases of a training testing curves. Every ML engineer loves ideal cases and always tends to move towards always opt for ideal cases. If we are following underfitting or overfitting decrease the number of people to the number of people where our model learns. For underfitting, I have already told you about. Now let's visualize the results. As you know, this this you don't need to know this code. This code is used for visualization of a gradient descent path, so you can understand how our parameters are decreasing. Now let's talk about it. As you can see, this is the space of MSC loss. This is the space of MSC loss, and this is the minima, or how this is our parameter first alpha. As you can see, 0, M is the weight, B is the bias, and MSC loss. As you can see, MSC loss. As you can see, MSC loss. So MSC loss here is here in the in Z6, and here you can see bias. Here you can see firstly our model starts from 0 comma 0. See, it starts from 0 comma 0. From 0 comma 0, it correctly converges, and finally it go towards the end. As you can see here, our model converges, and our M is 137 and B is 0.05. As you can see, it is near to zero point 0. So this is the case. This is the case. Here is our zero line. For bias, this is our zero line. As you can see, this is our zero line. Or for M, our zero line is this. Now some of you have a question about gradient descent algorithm. What if we have more than one minima? Let's see. What if we have more than one minima? Here we have M, which is the weight, B, which is the bias. Here you have MSE loss. Or here you have the gradient descent MSE loss curve. Here you can see the first minima and the second minima. As you can see here, it is the local minima, it is the global minima. And you can ask, sir, here two minima. So how our algorithm calculates the parameter M and B? Here, for example, let's tell it is M1 comma B1, and tell this it is M2 comma B2. So now it depends on our parameter initialization. For example, if we initialize the parameter at this point, so our current descent path will occur like this, in this way. As you can see, in this way, it will directly converge and at this place. If we have another one, if n is large at this point, then it is also converge and go towards this. For if someone have a question like, for example, it is at that place, now it depends on algorithm whether it go towards backward or frontward. For example, if n is large at here, so now it will go at this place. Now it go this place and it converts and end at this place. So in this way, it's based on our initialization. So what about our loss? Here we have less number of less loss, and here we have little more loss. So this is the limitation of our gradient descent algorithm, which is not a very good, which is not very good for our ML algorithm, but it also not do any significant loss towards our ML models. Now let's implement the using scikit-learn. Firstly, we will import these libraries: test free, linear regression, mean absolute, and mean squared error. Let's talk about mean absolute error. Mean absolute error. Mean absolute error. This loss function is average of absolute of difference of which is the summation I tends to 1 to n. This is our loss function. Here difference is y true minus y paired for I sample Now we are splitting the data in train and test set. However, we will use now we are splitting the data into train and test set. However, we are splitting those sets into single feature vector and multiple feature vector. For we are using two model and we are creating two model, but we are using the same model architecture, which is called linear regression model. In first model I will use only single feature. In second linear model I will use three features. So why same value? Now let's see. We have splitted that using train test split. Now let's change the now let's Now let's fit the model. We are fitting the model, which is training the model on trained data. Here also I will training the model on trained data. We are predicting the model using dot predict function on testing data. Here also predicting on test. For evaluating the model, I have vibrate, which is vibrate for every. See, you can see I have implied evaluating the model using mean squared error. MSC we are taking mean squared error. For mean squared error, you can see MSC loss is this, and for multiple for all feature you can see the MSC loss is this. You can see there is a difference of around 8 crore between single feature use and multiple feature use. Now let's implement the model function. You can see this is the linear regression model, which is equal to y mx plus c, or this is the linear regression model which is equal to y mx plus c. What is difference between both? Which is simple linear between both in this way. For the simple linear regression model, I have y1 y prediction function which is equal to m1 x1 plus c, and for multiple linear regression I have m1 x1 plus m2 x2 plus m3 x3 plus b. That is the difference between these three. So this is how our linear medicine is different in this both. Since you can see the single, but you can see the there is a difference between both function. Now, the final takings. I want to ask some question. Does we have a model performance increase after using multiple features? As you can see, of course. Is our model working perfectly? Think about it and ask yourself, is our model overfitting, underfitting, or ideal? Ask about yourself. We will splitting the data where test size is 20% of the total sample. You can see the 20% of is 90 and the rest 80% is training set. We are 5 features since we have selected 5 features. After splitting, we are doing feature scaling. We initialize the scaler and after initializing we are fitting on training value, and then after fitting on training value we transform the test x test value. Now we will fit the logic regression model. Now we'll fit the logic regression model. This is the model logistic regression model used for classification. Firstly, we will initialize the model and then fit the model and then predict on test. After predicting, we will evaluate the model using accuracy score, classification report, and confusion method. Before before moving toward, I will go back again to the notebook and tell you about some terms like precision, recall, and F1 score.
Now let's talk about precision recall F1 score. Before proceeding to our precision recall and F1 score, firstly we'll talk about four things which need to be understood beforehand. First is true positive, and second is false positive, and third is false negative, and fourth is true negative. First is true positive. True means actually the value of the parameters, and P means the model which is predicting. So for example, for example, we are calculating for diabetes prediction. We are calculating for diabetes prediction. For example, if a person is diabetic and our model also predicting diabetic, so which is the case of a true positive, and second is the case of a false positive. For example, actually the person is diabetic, but our model predicts it is no, the person is not diabetic. It is the case of a false positive and false negative. For example, if a person is not diabetic, but our model predicts it is if the person has a diabetes, it is the case of a false negative, and the case of a true negative. For example, if the person is a non-diabetic and our model also predicts it is non-diabetic, which is the case of a true negative, which is the case of a true negative. Now let's talk about precision. Precision means out of out of all people our model predicted out of all people our model predicted our model predicted person has diabetes. How many our model predicted actually the person has diabetes. Precision defines, for example we have 100 people having diabetes. 100 people having diabetes. So I 30 80 have actually have a diabetes, and our also model has also predicted those have diabetes. This is the case of a true positive. And 20 is the our model predicted not diabetes, but these are diabetes, which is the case of a false positive. So the precision is out of all people, out of all people our model predicted how many having diabetes, how many actually having diabetes. Now come to the recall. Recall means recall means out of out of all people out of all people who actually has diabetes, who actually has diabetes, diabetes, diabetes. For example, we have 120 people who actually have a diabetes, out of which our model predicted 80 have a diabetes, and also those 80 have a diabetes, so which is the case of a true positive. But rest 40, our model predicted they have not diabetes, but they actually have diabetes. This is case of a false negative. So recall is out of all people who actually have a diabetes. So how many our model currently identify diabetes? This is recall. Now F1 score is the harmonic mean of precision and recall. The more F1 score is balanced between precision and recall, the more good is our model is predicting, more good our model prediction is. For example, if our F1 score is zero point 0.9, so our model is very good. The more F1 score tends toward 1, the more our model working good. However, our mostly doctor prefers high recall. Mostly doctor prefer high recall because because why? Because missing a diabetic person which has a diabetes is very dangerous. But hospital prefer what? High precision. Why? You know about this?
Now let's talk about the classification report and confusion matrix. Here you can see the precision is 0.74% for non-diabetic, 86% for non-diabetic, and F1 score is zero point 0.8, which is very good. and for diabetic patient we have a less F1 score. So it is here we can signify our model predicting diabetes person less accuracy than predicting non-diabetic person in more accuracy. Here you can see the total accuracy of a prediction. This is the confusion matrix. Have I not told you about true positive, true negative, false positive? This is the confusion matrix. Here you can see this is true positive. This is what? This is true negative. This is false negative. This is false negative. This is false positive. So actually the false positive. What does false positive mean? Person is non-diabetic, but we said the person has a diabetes. The model says person has a diabetes. So now what do you mean by precision recall and accuracy score and F1 score? Accuracy and F1 score. Hope you now know about this. Now further discussion and comparison. Since we have tried and tested regression classification basic model, further junior you can do SVM, random forest, naive Bayes, DBS scan, gradient boost, random forest, SG boost, extreme boost, cat boost. You can do this algorithm for both classification as well as regression. You can also do some feature scaling, or you can also some feature engineering, or you can use normalization, which we have not used here. However, we have used scaling, feature scaling. Keep coding and meet you at induction. Thank you. This is the end of the lecture. Hope you all enjoyed it. Hope you all enjoyed. This is some of the pros and cons from style and without using the scikit-learn library or with using scikit-learn library. You can see common pitfalls and tips. You can see overfitting by the interfitting. We already talked about. So now the conclusion, what we have learned in this session. We have learned about regression, classification, and some concepts behind machine learning models. Now the further resources will be provided here. And at the last, thank you everyone and have a nice day.